This program is brought to you by Stanford University.
Okay, let's go back to where we were the last time. We were talking about the metric of space. Today what we're going to do is a little bit of geometry, and then we're going to get really into the dynamics of cosmology. The dynamics actually means how does the scale factor, we discussed the scale factor last time, how does it change with time? How does the universe grow or shrink or whatever it does? How does that take place with time? In other words, what's the evolution equations which govern how the universe expands, and if it eventually contracts, how it contracts. Those equations are known as the FRW, Friedmann-Robertson-Walker equations. Other people they're really the Friedmann equation. And we're going to study them tonight. But we're not going to derive them tonight from general relativity. We're going to derive them from Newton's equations. Newton's equations are enough to get us started. And then later we'll see how it fits together with the general theory of relativity. So let's begin with the idea of flat space, a geometry. Oh, well, first of all, we're always going to assume, unless I state otherwise, that the universe is homogeneous and isotropic. If it's homogeneous and isotropic, and it changes with time, then Hubble's law will always be true. Hubble's law that velocity is proportional to distance will always be true whenever the universe is homogeneous and isotropic.
Does that mean linearly proportional?
Yes. Distance, now that's a statement at a fixed time. The constant of proportionality, the so-called Hubble constant, depends on time in general. Only for very, very special situations is the constant proportionality constant. Generally, it's not. It's constant with respect to space. It doesn't vary from point to point. That's homogeneity. If you found different regions of space expanding differently, you would say that space is not homogeneous. So when one says the Hubble constant, I may sometimes lapse into calling it the Hubble constant. Keep in mind, it is constant with respect to position in space, but not constant with respect to position in time. All right, let's talk about the metric of space-time, given that space is flat. Can space, three-dimensional space, be flat and space-time itself be curved? The answer is yes. If you have a metric which is time-dependent, which describes flat spatial slices embedded in four-dimensional space-time, where the space itself may be expanding or contracting. In other words, the space may be thought of as an infinite flat rubber sheet, but the giants far away who are holding this rubber sheet are pulling on it in such a way as to expand it, contract it, make it time-dependent. Then the space-time itself is curved, but we'll come back to the curvature of space-time. Today I want to think about space itself. Yeah.
Is there any issue about the fact that the measuring rods are expanding too?
No, the measuring rods are not expanding, but the coordinates are expanding.
So objects are not, the space in between the molecules or whatever is not sort of expanding enough to make the thing expand?
Right. The forces which hold meter sticks together are far stronger than the forces which are the forces due to expansion. And so the meter stick is being held together in a way that, that is not expanding with the background space. But what is happening is disconnected things, like galaxies which are far enough apart that they don't feel strong gravitational fields between one another, they will be separating. All right? So objects which are large enough and diffuse enough that they don't feel any forces binding them together, those will expand with the expansion. But things like meter sticks, which are held together by strong electric and magnetic and electrical forces and other kinds of forces, those won't expand with the ambient expansion of the universe. All right.
You can't model it, though, as a force between points. Is that correct? Because otherwise it'd be an acceleration.
You can think of the expansion of the universe as a small force between points, let's say between atoms, okay? Yes, but a small force, imagine a small additional force. Imagine a meter stick. And now let's imagine a very small, very, very small force of repulsion, very, very small, of repulsion between the atoms. What will it do? Will it tear the meter stick apart? No. It might cause the meter stick to expand a little bit. Well, imagine for the moment a uniform, time-independent, small, extra repulsive force between atoms. All it will do is make the equilibrium position between the atoms slightly different. It'll cause, like having a spring. Supposing I have a spring connected to the wall, and it's a real good, hard, tight spring, so that in equilibrium, that spring is really small. And then let's add another small force pulling the spring away from the wall. Just another small uniform force, for example. What will it do? Will it cause this, the particle at the end of the spring to fly off and go flying off? No. What it'll do is it'll just change the equilibrium position by a little bit.
Is it so small that you can't, there's no lab experiment to detect it?
Well, it depends, of course, on the magnitude of the force versus the size of the spring constant. Right, right, that's right. The forces due to expansion are minute on the scale of ordinary matter. Far, far, far smaller, by many orders of magnitude smaller than the interatomic forces. And so, that's right, they could not possibly be measured in terms of a slight modification of the size of a meter stick.
But wouldn't that force, if there were no attraction between the things, wouldn't that produce an accelerated movement apart?
Accelerated or decelerated. If there was no forces between the objects, yes, they would expand with the expansion of the universe. In our universe, which is an accelerated universe, yes.
Well, if there's a force, it would seem as though, unless the force is changing, it would seem as though forces produce acceleration, as I recall.
That's right. Well, wait, what did you say? If there is no force, then there's an acceleration?
I'm just asking if the force, in fact, if that's the correct model, because a force would produce acceleration all by itself. It's not like a linear growth.
We'll come to it.
Okay.
Right. You are right. Expansion by itself doesn't create a force, but some kinds of expansion can be modeled in terms of a force, namely accelerated expansion. But we'll come to that. So our model of the world then is there are meter sticks which don't expand. Measured in meters and measured in meter sticks, the distance between galaxies does grow. And we can imagine coordinates which are embedded and expanding with the galaxies. We can also imagine coordinates which are not expanding. They turn out not to be as useful. So in that framework, every galaxy, to the extent that the galaxies don't have extra random, what's called peculiar motion, to the extent that the universe uniformly expands, each galaxy is located at a particular value of the coordinates, and that never changes with time. What does change with time is the meaning, the relationship between the coordinates and actual distances measured in meters. That relationship is codified by the scale factor. Okay, so let's begin then. We want to get somewhere tonight, so let's very quickly say, if I have a flat space, which I can just draw as a coordinate grid like that, then it has a metric, let's call it ds squared for spatial separation, for distance, for space. ds squared is some constant, any constant will do, let's call it a squared times dx squared plus dy squared plus dz squared, where a is just a fixed number. And what does it stand for? It stands for the distance measured in meters between neighboring points separated by a distance delta x equals 1. So if this distance, not this distance, but this coordinate separation is 1 unit on each side, then a represents the distance between neighboring points on this grid. And it goes out here in front in the metric. Right. Now, if the universe is expanding, then the distance between neighboring points on the grid will grow with time, and that means that a is now a function of time. A is a function of time, and that's the metric of space. That tells you the distance between points at a fixed instant of time. What about proper time? Let's go back over here to the special theory of relativity. In ordinary special relativity, the proper time between two neighboring points of space-time is given by dt squared minus the spatial distance squared minus, we might as well just call it ds squared, minus the space distance squared. That's the form that the metric of space-time takes, dt squared minus ds squared. In ordinary special relativity, we usually write this depending if we introduce the speed of light into the story, then this just becomes minus dx squared plus dy squared plus dz squared divided by c squared. That's the usual metric of the special theory of relativity. And by looking at this, we would just read off that ordinary special relativity corresponds to a metric like this. Well, the space components of the metric, the space components, ds squared, look like this. We would just say that a was 1 over the speed of light. But now we're imagining that a can change with time. When a changes with time, we have a time dependence there, and the metric of space-time now becomes d tau squared is equal to dt squared minus a of t squared times dx squared plus dy squared plus dz squared. So the metric of space-time is, first of all, time independent. It doesn't depend on x. The coefficients of the metric don't depend on position in space. They only depend on time. That's the homogeneity of the universe. Of course, in detail, the universe isn't quite homogeneous, and so really this is an idealization. And we could represent this by saying the metric tensor G mu nu has the form 1 in the time place, G naught naught, or G time is 1. That's the coefficient of 1. No off-diagonal elements. There are no terms like dx dy or dx dt. All the other terms are 0. All the other off-diagonal terms are 0. And the other terms on the diagonal are all minus a squared, minus a squared, minus a squared. And that would be the metric tensor, or the components of the metric tensor of this metric. It's a very, very simple metric. It's almost as simple as flat space-time. The only thing is that the relationship between the spatial measure and the time is time-dependent. That's a peculiar, yeah, okay. We can picture this geometry, the space-time geometry if we like, by imagining a time axis. This is just a cartoon of it. And now, at some early time, the coordinate grid might correspond to a fairly small spacing between neighboring galaxies. But as time goes on, the same grid corresponds to larger separations between galaxies. And if the universe continues to expand, then the grid would look like this. This is just a picture to focus your eye on what's happening. As time goes on, the sheet of rubber is expanding. And so the actual distance measured in meters, or centimeters, or whatever it's measured in, is expanding as time goes on. But this galaxy, this is Alice's galaxy over here. This is Bob's galaxy over here. Alice and Bob remain separated by 1 unit of coordinate. Increasing units of meters, but a fixed distance apart in terms of the coordinates that we're assigning. This is the way we're assigning coordinates, in such a way that each galaxy has the same coordinate value throughout the history of the evolution. Okay, so this picture goes with this metric. A is the actual distance between neighboring points. And as you can see, something rather dramatic happens if A becomes 0. In particular, if A in the past was 0 at some time, that effectively means that everything is squashed on top of everything else. Squashed in the sense that the number of meters separating Alice's and Bob's galaxies go to 0, which means Alice and Bob are squashed on top of each other. That's why one says that when A goes to 0, the density becomes infinite. So infinitely small A is something to watch out for. It means everything is crammed on top of everything else with infinite density. On the other hand, as A gets big, that means the coordinate mesh in units of meters gets huge, and it means everything is separating and becoming more and more diffuse.
In that equation, the small t, A of t, whose t is that? Does that make any difference?
No, it doesn't make any difference. You mean by whose t? No. Okay. So what do we mean by whose t? You mean which reference frame, or do you mean which units are we using for t?
What if it were a t riding on a light beam, then it would never change?
Right. Okay. Good. 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 This metric, this form of the metric, is only true in one frame, well, not quite only one frame of reference. This form of the metric, you can ask the question now, is this form of the metric invariant under some transformations? What coordinate frames, in particular, there are other coordinates in which the metric has exactly the same form. For example, if I just rotate the coordinates, In other words, that just corresponds to rotating the direction of x and y and so forth. The form of this metric would not change, and that's because dx squared plus dy squared plus dz squared is invariant under rotation. On the other hand, if I tried to make a Lorentz transformation, the form of this metric would change. There's only, at every point in space, we're talking about a particular velocity, a reference frame with a particular velocity, and what is that velocity? Physically, what does it correspond to? It corresponds to the velocity of the local galaxy. All right? So galaxies are moving apart, and we are following those local galaxies with coordinates embedded in the space, and the assumption is in that coordinate system, the metric looks like this. In some other coordinate system where you might be whizzing by the galaxies, or you might be rotating, your frame of reference might be rotating, it might be accelerating, it might be doing nothing more complicated than just moving relative to the galaxies. The behavior of this metric is different. Right. So in the coordinate system, which is moving with the galaxies, this is the form of the metric. Yeah, any other? Yeah.
So you wouldn't say it wouldn't be isotropic.
That's right. That's right. So this is the form of the metric in the frame in which the world is isotropic.
It seems to me you ought to say it's aging with the galaxies too.
What's that?
You ought to say it's aging with the galaxies too.
Well, I don't know the coordinate frames age.
I mean, the time factor has to.
What about this?
Yeah, that's the one that you have to, that has to be key to the galaxy's age, it seems.
Well, each galaxy carries clocks with it.
Exactly.
Right, and the clocks measure this dt. That's right. That's right. This t is the time measured by a clock moving, the clock made in the standard cosmic clock factory, where every clock was made out of the same materials, the same atomic clocks, for example, and this time is measuring the time in the frame of reference moving with the galaxies, which means it's the time each clock moving with the galaxies measures. Yes?
In this reference frame, the galaxy's motion is dt equals d tau.
Yes. That's right. That's correct. In this reference frame, time along the galaxy lines, time along the world lines of a galaxy is the same as proper time along the world lines of the galaxy. That's correct. Right. That's why it's what clocks measure. That's why it is what clocks measure. Yeah.
Are there transformations that leave this form of the metric invariant? You know, like the Lorentz transformation leaves the Minkowski metric?
Yeah, there aren't very many transformations. The presence of material in the universe, namely galaxies, breaks the symmetry and picks out a particular frame of reference. All right? Now, physics in this room is different because of our own presence, because of the material in the room. The equations of particles moving around, for example, would be different in frames of reference that were moving than in frames of reference that were standing still. For example, in a frame of reference which is moving rapidly, an object standing still in that frame of reference, okay? So we have a frame of reference which is moving rapidly relative to you guys. That's me, I'm moving rapidly. And I start juggling. Do I have to take into account my own motion? Well, the answer is, in practice, yes. Why? Because the atmosphere is not moving with me. So if I move fast enough, my juggling devices, juggling pins, or whatever they are going to be swept along by the atmosphere. Empty out the room completely and make a real, true vacuum, and then, or cause the air to move with me for some reason, but best to just remove the air and everything and make a true vacuum. Then my rules for juggling and the way I would juggle would be the same in the moving reference frame. So it's the presence of actual matter that affects the laws of physics, not the laws of physics, but the rules for juggling, for example.
You have to remove photons too, right?
Yes, you have to remove everything, absolutely. All right? So in this case, it is the galaxies themselves which are creating the metric. Remember, mass creates the metric, but if the galaxies are in a particular frame of reference, if they're homogeneously distributed and isotropically distributed, then in that frame of reference, this must be the form of the metric. As was mentioned, in another frame of reference, for example, a frame of reference moving along, the world would not be isotropic. All right, now, what we're going to do is first begin by studying Newtonian cosmology. Newtonian cosmology gets us a long way. It gets us to the basic laws of cosmology, to the basic laws by which the scale factor changes with time. Now remember, you can either think of the scale factor as something in general relativity, or you can just think about it as the distance between the neighboring galaxies. So let's take a Newtonian perspective on it, completely Newtonian, and see if we can work out how a Newtonian homogeneous and isotropic universe would behave. Right? See if we can find out how the scale factor would behave. So what are we starting with? We're starting with a world. I'm just drawing, that's a little patch of the world. I can't draw the whole thing on the blackboard. And the world is filled up with a gas, a uniform gas. And of course, that gas is not really a gas of air molecules. The gas points are galaxies. Galaxies, stars, and so forth. And it's pretty uniform. It's uniform enough on a large scale that we can pretend that it's just plain uniform. Now, let's place ourselves. Who are we? Are we anybody special? We're going to find out that the equations, although we're going to write them from our own perspective, from the perspective of somebody who, in his own egotistical imagination, is at the center of the universe, we're going to find out that the way the universe looks to us is exactly the same way as it would look to somebody else, that anybody can call themselves being at the center. But let's take the perspective that we are at the center, first of all, and let's write some equations. Oh, before I do that, what did we do here? I seem to have lost a page of my notes, and in fact, I jumped ahead of myself. My printer is it's got a nasty little demon in it which mixes up pages and loses them. Yes, right. How do the motion of the galaxies, what determines it in a Newtonian theory? Well, it's gravitation. The gravitation will tend to pull them together. That's basically what gravitation does. It's a pull. It tends to pull things together. And before we actually enter into cosmology, it's worthwhile talking first about the motion of ordinary particles in the gravitational field of a heavy mass. That's the starting point. That starting point is going to be useful in studying the rest of the universe. So let's just step back and think about a heavy mass point, or a heavy mass here. Some mass, let's call it capital M for the moment. Capital M. And imagine a second mass, small m, which has been ejected by force. By some initial impulse, it has been ejected away from the gravitating Earth, for example, or star, or whatever it happens to be. It's been ejected away by an initial thrust, but then just simply allowed to ride the gravitational field and do whatever Newton says it should do. Well, all we need to know, all we really need in order to go through and work out the cosmology of, in a few minutes, is we need to know energy conservation. That's all that really comes into the equations for cosmology, is energy conservation. All right? So what is the energy of this point mass which has been ejected away from this heavy static object? What is the energy of it? There are two kinds of energies that it has, kinetic and potential. Kinetic energy, what's the kinetic energy of this? mv squared, mass times its velocity squared. I'm going to assume that the velocity is radially outward. This is not correct. This is 2. This is small m. This is the kinetic energy of the outgoing mass. What about its potential energy in the gravitational field of the heavy object here? Anybody remember? Well, it's got the product of the masses. The product of the masses. It's got Newton's constant divided by the distance. I'm going to call the distance between them just d for distance. And am I missing anything? No. No. The force contains the distance squared. The potential energy only contains the distance. Okay? Not mg, not mmg divided by d squared. That's force. Energy, the potential energy, is just product of m's, g, and distance. That's all. One thing is missing out of this. Negative sign. Gravitational energy, gravitational potential energy is negative. Now remember, forces always push in the direction to decrease potential energy. The gravitational field of the Earth pulls in a direction which decreases the potential energy of this pen. All right? So force pushes you in the direction of decreasing potential energy. Did I get this? Sorry, it's plus, isn't it? Yeah. No, it's minus. It's minus. And it's minus because it corresponds to the force being attractive. Force being attractive makes it minus here. Putting this mass very close to the planet creates a large amount of negative potential energy. Putting it far away creates a smaller amount of negative potential energy. The energy becomes more negative by pushing towards here. So that's why the potential energy is negative for gravitation. Corresponds to an attractive force. And that's it. What does energy conservation say? It says that this energy doesn't depend on time. That's all. There might be many, many different objects ejected out from different positions, for example. Each one may have a different energy. When I say the energy is constant, I simply mean that the energy of this particular particle doesn't change with time. So, it's constant. Let's just call it constant. All right, now I want to play with this equation a little bit. Actually, not so much. For the time being, let's leave it the way it is. Now we come back. Yeah.
Does the potential energy increase with distance?
Yes. Yes. Let's see why that's true. Okay. First of all, let's plot 1 over d. Let's forget the constants here. Let's forget all the constants here. All right. Let's plot the function 1 over d. What does the function 1 over d look like? It looks like this, correct? It decreases at large d. You asked a question, so nod your head and answer if you understand. Okay. Here's d. 1 over d decreases with large d. But what about minus 1 over d? Minus 1 over d is exactly the same except upside down. That's minus 1 over d. All right? Which way does the force push? It pushes toward decreasing potential energy. So it pushes, if you like, toward smaller distance, or pulls. Equivalently, it pulls. So an attractive force corresponds to a negative potential energy, like this. All right, so this is constant, and this tells you some information. Let's talk about the different possibilities. The energy, let's just call it energy for the moment. We'll just call it energy. The energy has 3 possibilities. It could be positive, it could be negative, or it could be just plain 0. Those are the only 3 possibilities. Can the energy be positive? Let's imagine again the projectile being ejected away from the surface of the Earth or something like that. Well, if the potential energy only depends on the distance from the center of the Earth. D is the distance from the center of the Earth. That's fixed. It's fixed, let's say, at the surface of the Earth. By making the velocity sufficiently large, this term can easily be made to overwhelm that term. All right, just by making the velocity sufficiently large. In that case, the energy is positive. It starts out positive, and it must remain positive. Okay? So, yes, positive energy is possible. What about negative energy? Well, yes, you can have negative energy also. Supposing the starting velocity is very, very small. Even better, let the starting velocity be absolutely 0. Then this term isn't there, or it's negligible, and the potential energy dominates. In that case, for sufficiently small velocity, the energy is negative. Can the energy be 0? Sure. Just make sure that the velocity is just right to cancel this term at the starting point here. Just choose the velocity in such a way that these two are equal, and then the velocity is 0. All right, what is that particular velocity called that matches these two exactly? That's the escape velocity. If the velocity is smaller than the escape velocity, let's plot. Let's make a plot. This is distance, this is time. What happens to this projectile? Well, if the velocity is less than the escape velocity, we know very well what happens. You just fall back down to Earth. So let's start at time t equals 0 and throw our projectile up in the air with a small velocity. What happens? The distance begins to increase, and then it gets to the top of its trajectory and falls back down. If we throw it with even less velocity, it falls down even more quickly and doesn't rise as high. All right? What happens if we throw it with a humongous velocity, a huge velocity, huge enough velocity, and the energy is positive? In that case, we know what happens. We simply get ejected completely from the gravitational field of the Earth. And starting with a large enough velocity, there's some pull inward toward the surface of the Earth. And so there is some deceleration, but it's not enough to slow the spaceship or whatever it is down. And the spaceship or projectile escapes. It escapes and eventually moves off with a uniform velocity, which means a constant slope. Somewheres in between these two behaviors is exactly the right starting velocity to make the energy 0. If it were any less the velocity, you'd fall back down. If it were any more, you surely escape. That velocity is just the marginal separation point between escaping and not escaping. That is the escape velocity. And your distance just keeps increasing and increasing and increasing, but at an ever decreasing rate. So that's the escape velocity. This is E equals 0. This is E greater than 0. And these are E less than 0. All right, that's the basic decomposition of radial orbits into bound orbits, which fall back down, just at the escape velocity, where the distance just gradually increases, but with a slowing velocity, the velocity slowing down, but never enough to make it turn around. And then positive energy, where the projectile moves off with a velocity which doesn't get smaller. All right. The universe behaves the same way, or the equations of motion of the universe have the same property if the initial starting point has all of the galaxies moving outward relative to each other according to the Hubble law, but with a big enough Hubble constant, in other words, with a big enough velocity, relative velocity, then it will just shoot out and the galaxies will all escape from each other cleanly and with no tendency to fall back. If the initial outward velocity of recession is too small, then gravity will beat the outward motion and they'll all fall back in a giant crunch. The Big Bang will be followed by a big crunch. There is a point with the starting values of the velocity, which is like the escape velocity, which is just barely enough for the universe to keep expanding outward. Now, what I'm talking about now is Newtonian cosmology. Newtonian cosmology, there is a particular starting point for the velocities where you will do exactly the same thing as this escaping particle. In fact, we can use exactly this expression here, mv squared over 2 minus mmg over d equals a constant energy, to figure out exactly what happens to these galaxies here. And the trick is Newton's theorem. Let me remind you what Newton's theorem says. Newton's theorem is a remarkable theorem. Newton discovered it geometrically. We discussed it, I think, last quarter at length. I'll just remind you what it says. It says that if you have a spherically symmetric distribution of matter, in other words, think of yourself at the center. Well, you don't have to think of it. If there is a center, and if about that center the distribution of mass is isotropic, forget homogeneous. If it's isotropic, the same in every direction, okay, then the gravitational field, the gravitational force, here's our lump of matter, completely spherically symmetric, then the force on a particle out here is exactly the same as if all of the mass were concentrated at a point at the center. That's the first statement. All right. But the statement is a little stronger than that. Supposing the point in question was somewheres in the interior of this ball of material. The only restriction is that the ball of material be spherically symmetric. Then Newton's theorem says the following. It says that you can draw, where are we? Yeah, let's draw this carefully. We have a distribution of matter which is spherically symmetric. It doesn't have to be uniform. It just has to be isotropic relative to the center. And we place a particle over here. What is the gravitational force on that particle? And the answer is, you draw a sphere at the same radius as the particle, and you take all of the mass inside that sphere, and you pretend that it was localized right at the center of the sphere. What about the material outside that sphere? Newton's theorem says that it does not contribute to the force on a particle. In other words, all the masses at a distance larger than the particle cancel out when they contribute to the force of that particle. Only the masses on the interior, closer than the particle, contribute to the force. It's a remarkable theorem. In particular, it says something that at first sight does not seem terribly intuitive. Suppose you had a perfect shell, a perfect spherical shell of matter. Not a ball. A ball means that it's filled up solidly, but a shell of material, a thin shell of material. And you put a particle at the center. What is the gravitational force on it? It's clearly zero, because it doesn't know which way to get pulled, so to speak. What if you put it over here? It's also zero. It's also zero. The force, you might think that it gets pulled to the right because this mass over here is closer. Okay? But there's a lot more of the mass far away. The mass on this side over here, there's a lot of it. The mass to the right, there's only a little bit of it, and they cancel. What happens if we look at if we take the particle outside the shell? What is the force on the particle outside the shell? Exactly the same as if the entire shell were concentrated at a point. That's Newton's theorem. The reference for it is the Principia, and you don't even need calculus for it. On the other hand, not using calculus makes it incredibly difficult. Okay. The story is, I don't know what the actual truth of it is, but that Newton, of course, invented the calculus for purposes like this, worked these things out using calculus, but of course he knew that all his compatriots, all his enemies, didn't know calculus, and so in order to convince them of the truth of his theory, he worked out everything using only Euclidean geometry, and that's why the Principia is so hard to read. Yes, okay, this is a theorem. All right, now let's pick, just for simplicity, let's pick a galaxy or a mass moving with the galaxies. Let's pick it along the x-axis, although that's not important. Since everything is isotropic, it doesn't matter which axis we pick. But let's pick our mass along the x-axis, and it's at coordinate x. Let's work out Newton's equations. Yes?
What's the meaning of spherical symmetry in a homogeneous distribution?
Well, it means anybody looks around and sees everything the same in every direction.
No, not isotropic, homogeneous, I meant.
What is the meaning of homogeneous?
Well, I'm just saying...
At the moment, I'm not using homogeneous, but I will.
Well, I'm just having trouble visualizing what the shells would be in a homogeneous universe, because it's sort of... I don't know what to neglect.
Well, so far I haven't introduced any shell into this.
Okay.
I will, but not yet. Yeah. Mm-hmm. Yes.
In the example you gave there, should we be a little surprised that it seems like as the particle moves across the boundary, the force is discontinuous?
I don't know if you should be surprised. It's a true statement. Of course, boundaries are not really infinitely thin. They do really have a distribution. A shell, of course, has some thickness, and so everything would vary continuously. But, if you had a very, very thin shell, yes, the force would vary discontinuously. Should you be surprised? Yeah, I would say yes, you should be surprised. It is a little bit surprising. Of course, when you think about it enough and you work out the equations and you get familiar with it, it's less surprising. It's incidentally very special to the 1 over r squared Newtonian force law. It would not be true with other force laws. Other force laws do not have this property. This is the 1 over r squared force law has this property. All right. I'll tell you what the mathematics of it is. The mathematics is fairly simple, and or a picture of what's happening. If you imagine a mass point, instead of a mass point, imagine that it is a flow of water which is materializing at this point. It could be coming in from behind the blackboard, a little pipe ending here, and the flow of water flows outward. Outward in the plane of the, how does the velocity of the flow decrease with distance? Well, it decreases with, in 2 dimensions it's 1 over r, in 3 dimensions it's 1 over r squared. So in 3 dimensions, in other words, if at some point of the world a flow of water flowed out away from some point, the velocity field would be 1 over r squared. Okay? Now, imagine that we put one of these little spouts at each point around the circle continuously, so that around on the circle here, there was a continuous distribution of flow of water out of that circle. Right? The water completely fills everything, but what is the velocity of the water in different places? Well, on the outside of the ring, the velocity is flowing outward, and it flows outward with a velocity that's exactly the same as if the same flow of water materialized at the center. But what about inside this circle? Can there be any flow of water? Which direction would it flow in? If it flew out radially, where would it be coming from? Supposing the water flowed out here. How could that be if there was no source at the center? How could it possibly be that there would be water flowing away from the center if there was no source of water at the center? Right? That's essentially, so the answer is that in the interior of this shell of sources of water, there would be no flow. It would stand perfectly still. But the second you move to the other side, you would see a flow which is exactly the same as if all the source were concentrated at the center. If you think about that for a little while, you'll get the reason why the 1 over r squared force has this surprising Newtonian property. But our purpose tonight is not to derive it. We discussed it earlier in the class. I think we even derived it. We're going to use it. We're going to use it to study cosmology. And to use it to study cosmology, we just pick a point away from the center being arbitrary, but nevertheless, pick a center in the frame of reference where the center is at rest, right at the center, where this blue galaxy here is at rest. Pick that point and we'll apply Newton's equations to another second point, which is at coordinate x relative to, this is x equals 0 over here, and this is x equals whatever it is over here. All right? So how do we find the force on this particle over here? Well, what we do is we draw a sphere. Knowing that everything is isotropic, we can draw a sphere centered at x equals 0, and using Newton's theorem tells us that the force in this frame of reference at rest with respect to this galaxy, the force on the other galaxy over here is exactly the same as if all the mass on the interior of this red shell were concentrated right at x equals 0, and all the other galaxies on the outside don't exert any force on it. In other words, for a galaxy at point x, it behaves exactly as if the entire mass within this sphere, were concentrated at the center, and as if there were no other mass on the outside. So let's, for the moment, call the mass concentrated within this sphere. And notice the sphere grows as if x increases. Of course, the sphere will grow with x. The sphere always surrounds the same number of galaxies. If the galaxies are separating apart, the sphere grows. That sphere always contains the same number of galaxies and therefore the same total mass. So let's call the mass within that sphere capital M for the moment. It's the mass within that sphere. Then the motion of this point follows exactly the same law. Where is it? We erased it off the blackboard. Let me write it out again. 1/2 mv squared, where v is the outward velocity of this point, minus capital M, little m, g over the distance is equal to something which is fixed with time. All right? Fixed with time does not change with time. For that particular galaxy, let's just call it the energy, or let's just call it a constant. All right, just to save myself some confusion later, not confusion, but just to save some steps, let's multiply this equation by 2. And it just becomes mv squared minus 2m little m g d is equal to twice a constant, but twice a constant is just another constant. So the way I've written it here with the 2 here is exactly the same equation that I wrote before. Okay. All we have to do to implement this equation is find out, to try to figure out what the velocity of this particle at point x is. And here is where the Hubble law comes in. What does the Hubble law tell us? Well, even before the Hubble law, yes, all right. Let's begin not with the Hubble law, but with the actual physical distance. I suppose we should give these galaxies names, Bob and Alice. Bob thinks of himself at rest, and he sees Alice moving away. The distance to Alice is equal to x, but not x. X has to be multiplied by something. A, the scale factor, as a function of time. What about Alice's velocity relative to Bob? That's velocity. That's equal to the time derivative of d. Now, does x change with time? No, x is just the coordinate fixed, embedded inside Alice, moves with Alice. So x does not change with time, but a can change with time. That's equal to x times a dot of t. Let's use that in this equation over here for this particular galaxy. This is all we need. Incidentally, yes, let's go one step further before we move to this board. Let's go back to this board, and let's divide by the mass of the projectile particle. The mass of the projectile particle is also a constant. That means the constant divided by m here. M appeared in both these terms here, and the right-hand side was just a constant. A constant meant constant with time. What is a constant divided by m? It's also a constant. So I can just call it constant. I don't need to write constant over m. All I need to remember is that the left-hand side does not change with time. It's equal to something which is constant with time. When I say constant with time, I don't necessarily, constant with time. Okay, let's plug in here and see what we get. The square of the velocity, that's the first term here, velocity squared. Velocity squared, that's x squared, that's fixed, that's constant, times the square of the time derivative of the scale factor. Remember what we're trying to do. We're trying to figure out how the scale factor changes with time. Well, a dot is how the scale factor changes with time. So far we don't have an equation for it. I've just written down a dot. There's also x squared here, which depends on which galaxy we're talking about. Different galaxies, different x's. Okay, now let's write down this term, minus twice g. The distance is x times a. But what about the mass within here? The mass in here is not just a number like the mass of the sun. It depends on how big this sphere is. How big, it depends on how many galaxies are inside it. It depends on how many galaxies are inside it, basically. The number of galaxies inside that sphere stays fixed with time because the sphere grows with the galaxies. It's fixed to pass through Alice here. As Alice moves away, the sphere grows, but the galaxies don't move out of that sphere. They stay inside that sphere for all time. And so the mass within that sphere stays fixed with time. But depending on which sphere we were to take, this sphere or this sphere, that mass would change. So here's how we figure out the mass. We say, supposing, using the idea that the universe is homogeneous, we say there is a well-defined, at every instant of time, there is a well-defined mass per unit volume, a density. Okay? A mass per unit volume, a density. So in order to find out the mass in the sphere, we need to take the density, let's call it rho. Rho is the density, the number of kilograms per unit cubic meter, for example. Rho is density. Let's write it here. Rho equals mass density. And what do we multiply it by in order to get the mass within the sphere? Right, the volume of the sphere. You jumped ahead of me, right. The volume of the sphere. And the volume of a sphere is 4/3 pi. X cubed, a cubed. X cubed times a cubed. D cubed, if you like. Right? D cubed, which is x cubed, a cubed. All right, so 4/3 or, yeah. All right, so let's put it together. Let's combine it. So it's a mess, but let's put it together. Oh, sorry, we have the right-hand side. The right-hand side equals a constant. Okay. Any questions? Say it again?
Rho changes with time.
Rho indeed changes with time, and we're going to worry about rho changes with time. Why does rho change with time? Yeah, because the galaxies separate, and so it becomes less dense with time. But at any given time, it's the density that goes here. Okay, this term has an x squared in front of it. Oh, one other thing. Rho may depend on time, but it doesn't depend on position in space. So it doesn't, what principle is involved there? Homogeneity. So it doesn't depend on which x we're talking about, but it does depend on time. All right. Now, let's simplify. X cubed, a cubed over xa, that's just x squared, a squared, right? Notice that both of these terms contain x squared. The other things that it contains do not depend on where you are, which galaxy you're talking about. A is the scale factor, that's the same everywheres. G is Newton's constant, that's the same everywheres. Rho is assumed to be the same everywheres. Certainly 4, 3, and pi are the same everywheres. The only thing that varies from place to place, here, 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 is x. So the left-hand side is proportional to x squared. That must mean that the right-hand side must be proportional to x squared. Now, wait a minute. I said it's constant. How can it depend on x squared? What did I mean by constant? I meant that it doesn't change with time. For each x, it doesn't depend on time. But in order for this equation to make sense, this constant must also be proportional to x squared. So that means in order for the equation to make sense, the energy of, and that, remember the right-hand side is related to the energy of more distant particles must be larger than the energy of the closer ones. But that makes sense. Of course it does. They're moving faster. So this constant, what I called constant over here, is really a constant with respect to time times x squared. Otherwise, the equations couldn't make sense. Once we assume that the equations make sense, then you can divide away x squared. And notice what you have, and this constant now is a constant both with respect to space and time, what goes over here. Okay. Now we have something interesting. We have an equation which doesn't depend on which galaxy we started with. It does, and which galaxy we're talking about. I could have put us at the center and studied Alice's galaxy, or Fred's galaxy, or Michelle's galaxy, or George's galaxy. No, George's galaxy is out there. Anybody's galaxy we like, we would get exactly the same equation. It depends on A, it depends on time, so it's an equation for A as a function of time, but it doesn't depend on which galaxy we started with as the center or which galaxy we studied as the one moving relative to the center. So we've managed to invoke a set of assumptions which gives us a simple, clean equation for the way A varies with time. Now, it depends on this constant on the right-hand side. It depends on the constant at the right-hand side. Just in order to put it in a more standard form, I'm going to put it in a more standard form now. The standard simply means historically standard form. Standard form involves transposing this piece to the right and dividing the whole equation by a squared. So let's do that. If we divide by a squared, we have a dot squared over a squared equals, I'm transposing this to the right, equals 8 pi g over 3. 8, 2 times 4, pi over 3, 8 pi g over 3, rho, the density of mass, that's all from that term, that's it, right? Plus, and on the right-hand side, plus constant, I'm now going to call that constant minus k. Now, does that mean that the constant is negative? No, it could be positive or negative. Or that is to say, minus k could be either positive or negative, or 0. I have not biased it by writing minus k here. There's nothing special about k being positive or negative. It's a historical terminology. K here can be positive, negative, or 0, and divided by a squared. Where did the a squared come from? It came from the fact that I divided the equation by a squared. These are very famous equations in cosmology. They're called the FRW equation, these equations. This equation is called the FRW, Friedmann-Robertson-Walker. Friedmann is spelled with one E and one I. F-R-E-I-D-M-A-N, Alexander Friedmann. And who Robertson and Walker are, I don't know. They were Johnny-come-latelys in the business. I don't know how they got into it, but there was Alexander Friedmann very shortly after Einstein's. He derived it from the general theory of relativity. I don't know why these equations weren't derived by Newton. Newton wanted the universe to be static and eternal and stay there forever and ever. And he made some mistakes along the way in order to, he didn't make mistakes. He just thought it should be and knew there was something wrong with his own equations. No, knew there was something wrong either with his equations or his assumption. In any case, what does this equation tell you? It tells you that if there's any mass density here, in general, unless these two exactly cancel, but they won't cancel in general, these two, that A will depend on time. The left-hand side in general won't be 0, and it'll depend on time. And that means the universe will either expand or contract or whatever it's supposed to do. These are the FRW equations. Now the problem is, supposing I sent you home to solve this equation, the first thing you would tell me, you would ask me, I think, is what is rho? Can we just put a number in for rho? Anybody have any idea at all what the density of material, average material in the universe is today? I don't. I just wonder if anybody does. I think it's more like about 50, but you know, it's a small number of protons per cubic meter. It's a very, very small number, but that's okay. It's a small number is all right. But it's not time independent. It won't stay that way. As things expand, the density will decrease. As the density decreases, what goes in here will depend on the scale factor. So there's a hidden dependence. There's an equation here involving the time derivative and so forth, but there's a hidden dependence on the scale factor here that we have to unravel if we want to solve this equation. Another thing we have to decide is what value of k to put in there. Now remember, remember now, k was like the energy of this particle that was ejected away from you. It could be positive, negative, or 0. Yeah?
Actually, m was a function of x only.
M was not, M?
M was a function of x
Yeah,
only
yeah.
and not of time. So
Yeah.
we could have gotten rid of it
Yeah.
by just saying we can calculate n at any instant of time.
Yeah. Yeah. I went through, you're telling me I went through what is essentially an extra step of introducing rho. I did it, yes, you're right. I could have used m divided by volume. Okay. I didn't do that because I wanted to put it in a standard, I wanted you to get familiar with this particular form of the equation, which depends on the density. All right. The other thing one has to decide is what about k? It's a constant, but it could be positive, negative, or 0. Let me remind you what that means. Well, if minus k is positive, it means it's like the situation where the particle is receding with greater than the escape velocity. In that case, the universe just continues to expand forever and ever, doesn't slow down. There may be some initial deceleration for the same reason that if you shoot something away from the Earth, at first it will decelerate because it's being pulled, but as it gets further and further from the Earth, the pullback becomes more and more diminished, and it'll just shoot off with a more or less uniform velocity. Okay? So if minus k is positive, that corresponds to the positive energy situation. The universe just continues to grow, and gravity eventually becomes irrelevant, and everything shoots apart with uniform velocity, or uniform. That's number one. Number two, we have to do something about figuring out how to express rho. But the only other thing I wanted to point out is that this a dot over a, well, it's actually squared over here. But the last time I told you another name for a dot over a. A dot over a was the Hubble constant, which isn't constant with time. It was the Hubble constant. So another way to write this is that the Hubble constant squared is equal to 8 pi g times the density of material minus k over a squared.
Is rho proportional to 1 over x cubed here?
1 over a cubed. 1 over a cubed.
Yeah.
We'll come to the top.
You got rid of, how did you get rid of the x in the equation?
Dividing by it. x squared, and also the other term which I've erased off here, the constant term, I said has to be proportional to x squared if the equations are to make sense. If the left-hand side is proportional to x squared, the right-hand side must also. But you can kind of check it. You can check the fact that as you move away, if the Hubble law is satisfied, then obviously the further away you are, the faster you're moving, and so the energy will depend on where you are, and it will depend on it in the right way to make this x squared over here. So we just got rid of the x squared by dividing.
Does the constant have units? I mean, we start out with energy, but we canceled out this was squared. And
the constant in this form does not have units. Okay. Again, I'm going to assume the speed of light is equal to 1. What are the units of A? Meters, or length. Oh, I'm sorry. Yeah, no, that's right. What about the dot? What are the units of dot? A dot is length over time. All right. Now, in units in which the speed of light is equal to 1, length over time is dimensionless. If we measure space the same way we measure time, then A dot is dimensionless, and the left-hand side has units of 1 over A squared, 1 over length squared. Here's a 1 over length squared here, so that means that K is dimensionless. K is dimensionless, has no dimensions. You can check that this thing has the same units over here. But let's talk now about rho. What do we know about rho? Well, let's take a cubic cell of space, and now let's let it be 1 unit of coordinate on a side. A cube of space, a unit cube, where x is equal to 1, y is equal to 1, and z is equal to 1. So it's a cube. It's not a cubic meter in size. It's just a cube in coordinate space, 1 unit on a side. And let's suppose that there's a mass m inside it. Okay? So in a cubic coordinate volume, 1 coordinate unit on a side, let's suppose there's a total mass m. How much mass will be there later in that same cube? The same amount, because the cube corresponds to an expanding cube. The galaxies expand. The galaxies don't expand, but the difference between them expands. The number of galaxies in there stays the same, and so that mass is fixed and stays the same for all time. What is the density? The density is the mass divided by the volume. Okay? Is the mass in there divided by the volume. What is the volume? A cubed. So that's rho. Now, in terms of m, we of course have to know at some point in time, we have to know what the mass inside a cubic volume is. That's a parameter. There are a number of parameters that go into here, which are numerical parameters which determine the behavior thereafter. We don't get a completely free lunch here. Yeah.
According to that equation, the Hubble constant is functional rho.
Yeah. Mm-hmm.
Therefore, it's not a constant.
That's why I keep telling you the Hubble constant is not a constant.
It's functional rho, and rho changes.
Right. The Hubble constant is not a constant.
But it's not.
final examination is going to consist of one question. Is the Hubble constant a constant? That's right. The left-hand side is not constant, and the right-hand side is not constant. All right. Choices that have to be made. The amount of mass in a cubic unit volume, whether K is 0, positive, or negative, and what its value is. And that's about it. That's about the only arbitrary things in this here. All right. K equals 0 corresponds to the universe being exactly at the escape velocity. If things were shot out a little bit slower, things would crunch a little bit faster, they would just recede off, and at K equals 0, they just move away, but at an ever-diminishing velocity. Now, keep in mind, this, at this stage, is a model, a Newtonian model of a cosmology. It doesn't contain yet certain features that the real thing has. Yeah.
If K equals 0, then the velocity between two galaxies is approaching 0.
Approaching 0.
Is it approaching 0 in such a way so that the distance between them is bounded or unbounded?
Unbounded. Unbounded. Same as the particle being ejected from the Earth. It slowly, no, it couldn't possibly come to a rest. If it actually at some finite time came to rest, it would fall back in. So it slows down, yeah, right, it slows down, but with the distance ever increasing, but more and more slowly. So the velocity goes to 0, but the distance does not go to a constant. We can work out how it behaves. I think the distance grows logarithmically. The distance grows logarithmically with time. Yeah, the distance is unbounded. Yeah, but the velocity goes to 0.
The velocity is asymptotic to 0, whereas if the energy is positive, the velocity is asymptotic to something greater than 0.
Right. Exactly. Right. That's correct. Okay. Before settling on K, let's plug into this equation rho equals m over a cubed, and m is just a parameter. It's a parameter that has to be determined by observation, if you like. Right, then this equation becomes m, and it's not the mass of the sun, and it's not the mass of the galaxy, it's just the mass in the cubic region of space, 1 unit on a side, divided by a cubed. And that's it. That is the Friedmann-Robertson-Walker equation, the so-called matter-dominated case. We'll explain what that means later. Okay, what about K? We can make various choices. The simplest choice is K equals 0. That's the case where everything is exactly at the escape velocity. And it's simpler only in that the mathematics is simpler if I set K equals 0. It's obviously simpler. There are fewer terms in the equation, that's all. The equations are easier to solve. So I'm going to take you through the solution of the equations in the specially easy case where K is equal to 0. That's just at the critical velocity. And we'll see what happens. Okay, so let's rewrite it. A dot over A squared is equal to 8 pi mg divided by 3a squared, a cubed, excuse me, a cubed, period. That's it, when K is equal to 0. The equations with K are a little harder. They're harder to solve, but not that much harder to solve. Okay, how am I going to solve them? I'm not going to spend a lot of time solving different. This is a differential equation for A of t. The A dt is equal to, no, it is what it is. I'm going to solve it by guessing the answer and then showing you that it solves the equation. This is one way of solving the equation. All right? This is the way people usually solve equations, and then And, all right. We could try various things. We could try A is a power law. We could try an exponential. We could try all sorts of interesting functions. A power law is usually the first thing you try. The power law means that A increases or decreases. Incidentally, okay, now we can see something interesting. The right-hand side here is never zero and it's always positive. The left-hand side is always obviously positive. It's the square of something. But it could become zero. How could it become zero? If the universe expanded and then recontracted at exactly the point where it turns around, A dot would be zero. All right? But the right-hand side is not zero, never zero. So that means this universe cannot turn around and contract. Either it's growing or it's shrinking, and it stays that way forever. It either is eternally growing or eternally shrinking. Well, it can't eternally shrink because it'll shrink to a point, but it can eternally grow, and that means that A dot over A is positive. It means the universe grows forever. All right, let's try some things. How about A grows like T? A is proportional to T. There's a possible answer. Well, it won't work, but let's jazz it up a little bit. We could try T squared, we could try T cubed, we could try T to the 4/9, we could try T to the pi power, we could try all sorts of things. Let's just call it T to the power P and try to figure out what P has to be to solve the equation. No? Let's also be a little more general. How about putting some constant, unknown constant there? And see if we can plug this formula into the equation and determine what the two unknown constants are, and check that the equation is solved by those appropriate constants. That is the way I am quite certain this equation will solve the first time. Just try some simple solution. This is a very simple thing to start with, and it is the solution of the equation with appropriate values of P and C. So let's try it. First of all, what is A dot? The time derivative of A. All we have to do is differentiate this. The C, by assumption, now is a constant. It may work out that you can't solve the equation this way. Then you'd have to start modifying. But let's check. A dot is equal to C, P, T to the P minus 1, right? Everybody agree with that? Okay. What about A dot over A? A dot over A, let's divide by A. A is C T to the P. Well, first of all, the C's, the constant C, cancels out. That's nice. It'll come back. That cancels out. What is T to the P minus 1 over T to the P? 1 over T. The P's, the T to the P's cancel, and you're just left with T to the minus 1, which is 1 over T. That's A dot over A. It's always proportional to 1 over T with the power law. The power enters just in the numerator here very simply. Okay, let's write down the equation now. A dot over A squared, that's P squared over T squared, right? P squared over T squared on the left side of the equation equals 8 pi mg divided by 3, and now C cubed T to the 3p. All right, I've just cubed A. A is C cubed times T to the 3p. Okay, that goes here. A cubed is C cubed T to the 3p. First question, can the left-hand side and the right-hand side possibly be the same? How can it be that something which goes as 1 over T squared can also go on the right-hand side as 1 over t to the 3p. If p is 2/3. 2/3? Yeah. That's the only way. So the first thing we find out is that this equation can only be solved if p is equal to 2/3. Yeah, 2/3. If p is 2/3, then what appears here is just t squared in the denominator, same as the t squared here. So that's the first piece of information we learn, that the universe expands as the 2/3 power of time. It doesn't expand linearly with time, a growing like t. That would be sort of unaccelerated motion. It expands less rapidly than that. In fact, it slows down somewhat. So it's t, so we can now replace t by 2/3 everywheres. Well, if we choose t to be 2/3, then the time dependence on both sides of the equation is the same. That's been guaranteed. And so I can cancel the time dependence. T to the 3p just becomes t squared. And I can now cancel it. And lo and behold, I have a formula. Now p squared is what, 4/9? P squared is 4/9. And now I can solve this equation for the unknown constant c. What is it? C cubed is equal to 9 times 8 is 72. Well, 9 times 8. 9 times 8 pi mg multiplied by 9 divided by 4. Have I left any? Is that it? 3 on the bottom. 9 times 8 divided by 4 times 3 is 6. So I then determine c. It's guaranteed that the equation is solved by this assumption. A equals 6 pi mg, the cube root of that. That's the cube root of that. That's A. Does it solve the equation? You can check that it solves the equation, but you'll just be going back through the same steps that we did. Okay? It does solve the equation. In fact, it's the only solution of the equation. It's the only solution of the equation. And it tells you, the most interesting thing that it tells you is that the universe continues to expand, expands as the 2/3 power of time. Okay.
Shouldn't there be an unknown constant?
Yeah, the unknown constant can be absorbed into a shift of what you call t equals 0. Notice that at t equals 0, the scale factor goes to 0. The unknown constant, whenever you have there is an unknown constant, but you can put it into the form t minus some t0 to the 2/3. That becomes the unknown constant, but then it's just a shift of what you call t equals 0. That's the only unknown constant. So once you say that t equals 0 corresponds to the time at which a is equal to 0, there's no more constants left. All right, well, first of all, among other things, it tells us that if we go back in time to a certain time, namely t equals 0, a will be equal to 0. A equals 0 is this crazy condition where everything is squashed on top of everything else, and the density becomes infinite. Right? So if you like, the time, and that, of course, is what we refer to as the Big Bang. The Big Bang is when to say 0 is probably extreme. We don't know what happens to matter when it gets too dense, but at some time, A was so small that everything was so crowded atoms were crowded on top of atoms, nuclei were quarks crowded on top of quarks, and it was a solid, dense configuration. That's time t equals 0, when the scale factor is 0. This t here is the time from that particular era, when things were very, very crowded. Okay. Now, this, as I said, first of all, this is a model that does not capture some of the physics. It captures some physics, not all of it, but it captures enough to note some interesting fact. Let's come back over to here. A dot over A is the Hubble constant. That's the Hubble constant. On the right-hand side, we have 2/3 T. Now, as has been pointed out, the Hubble constant depends on time. Yes, it does. Here it is. How does it depend on time? Like 1 over the time. But here's a tool that you can now use. The Hubble constant today is 2 divided by 3 times the age of the universe. That's what T is. T is the time from the Big Bang. And the Hubble constant is simply almost just 1 over the age of the universe. Approximately, apart from this factor of 2/3, the Hubble constant is 1 over the age of the universe. The age of the universe. So if we know the Hubble constant today, we can tell what the age of the universe is, or at least we can trace it back to the point where our equations might not make sense because they're too Newtonian. They don't take into account quantum mechanics. When matter gets very close together, new things happen. But we can trace it back as far as the equations make sense and say, how long ago was the universe ejected from this very, very dense state? All right, we measure the Hubble constant. We know what the Hubble constant is just by astronomically measuring the distance and the velocity of distant galaxies. I never remember what the Hubble constant is in any kind of what are the units? It's meters per second per second. No, meters per second per kilometer. No, meters per second. It's given in ridiculous units, astronomers' crazy units. What I do remember is the age of the universe. All right? Right. What I do remember is easier for me to remember the age of the universe than the Hubble constant as given in astronomers' peculiar units, kiloparsecs per something. And what is the age of the universe? Again, it's measured by measuring the Hubble constant, distance and velocity. And the answer is, give or take a few years, 13 billion years. Well, somewhere between 13 and 14 billion years.
You said K equals 0. That's pretty realistic?
It's pretty good. Yep, very realistic, in fact. We measure that constant K in microwave anisotropy experiments, and to the best of any measurement at the present time, K is 0. It's 0 to within about 1%. Okay, but that's No. The 1% is a bound. In other words, we know that it's not bigger than 1%. It's not bigger than 1. That's small. And we're going to talk about what K really means, but let's put it this way. High precision cosmology, and it is now a reasonably high precision subject, is still consistent with K being 0. There's no known deviation from K equals 0. Yeah. The reasons for that, yeah.
I'm just a little confused about what M is. It was the mass inside an arbitrary volume.
Yeah.
An arbitrary.
Yeah. Yeah. So we ought to come back to what's right. Right. A also has a degree of arbitrariness. Why? Because there's arbitrariness on both sides. The real thing which is not arbitrary is A divided by m to the 1/3. All right, now why is this particular combination the physically relevant or physically meaningful? What is A? A depends on your choice of initial grid. I could have taken this box to be the distance from us to Andromeda. I could have taken it to be the distance from us to the Coma cluster, or whatever. The equations are always the same, but the amount of matter within a box depends on which box I choose. Right? Supposing I double the size of the box of my, let's call it the fiducial box. Supposing I double the size of this basic box, what happens to m inside it? It gets multiplied by 8, right? Right. What happens to A divided by m to the 1/3? It doesn't change. Okay? So this is really the quantity which is independent of your choice of conventions for how you choose the grid. Double the size of the grid, A becomes only half as big as it was. Is that right? No. Double the size of the grid, A doubles. I'm sorry. Double the size of the grid, A doubles. The mass goes up by a factor of 8, but the mass to the 1/3 goes up by a factor of 2. So this is the form, this is the quantity which is independent of the choice of grid. Does that answer your question?
It confused me now about what I thought A was.
A is arbitrary to some extent. A is arbitrary.
A over m to the 1/3 is
A over m to the 1/3 is related to m over A cubed, is it not? Yeah. Right. This is the density, and that's the thing which is physical. That's the thing which has real physical meaning. The amount of mass within...
well, not A, X, right?
No, m was defined to be the mass within a unit box. Yeah, with an A cubed box, right. Okay. So it is the real physical density of matter. This here is, right. It does change with time. Of course it changes with time. It grows like t to the 2/3. But at any given time, this quantity is independent of the way you choose the grid.
But if you're going to use A to compute the age of the universe, you need to have a number for m.
No, actually you don't. Here's what we discovered. Quite apart from what m is, we always found that p was 2/3, right? That was independent of m. So that says that A is equal to some unknown constant. The unknown constant C depends on m. Right? C times t to the 2/3. Okay. The unknown constant C cancels out of the age of the universe. A dot is equal to 2/3 C times t to the minus 1/3. Is that right? I've just differentiated it. The Hubble constant, which is A dot over A, is just 2 over 3t. The constant here cancels out. The constant cancels out, and with it cancels out the dependence on m. So it's quite remarkable that the calculation of the age of the universe doesn't depend on the density of mass. At least the calculation in terms of the connection with the Hubble constant. The connection between the age of the universe and the Hubble constant and so forth is independent of...
Is that sort of because the Big Bang happened such that the k equals 0, and then therefore we can now ignore c? I mean, it all cancels. If k was different from 0, then
it would be a little bit of dependence. Yeah, that's right. If k was not 0, there would be a little bit of dependence.
It's having the
this
set K equals 0.
When was the
FRW equation?
when was it?
When was the map? When did they publish it?
Well, Friedman was killed during World War I. Einstein invented the general theory of relativity around 1915. That doesn't leave much of a window. Somewhere's in there. Everybody know when World War I was? Ended 1918? Yeah. So, right. Now, Friedman didn't have all of this quite as in the form that I have it. Exactly. The history beyond that, I don't know. I don't know who Friedman and Robertson Walker were. I'm sorry, I don't know who Robertson and Walker were. I'm not sure. I'm sure they played some key role in putting some of these together.
This all seems to depend on an assumption of an open universe.
Yes, it depends on the universe being flat. I've used flat geometry, flat spatial geometry. We're going to come to that. We're going to come to that. The three possibilities, k equals positive, negative, or 0, correspond to flat space. K equals negative is negative curved space, and k equals positive is positive curved space. So that does depend on the universe being flat. Yeah. I want really, in this form, I suspect that the history really doesn't go back past the acceptance of the Big Bang Theory, which was sometime in the 60s, in this precise form. This form has been sort of set up to be useful. It's been set up to be useful. The things that are in it are the density of matter, the scale factor. How much of it Friedman actually wrote down, I don't know. Yeah.
The flatness of, you start off by talking about flat space, right, and you use that assumption in estimating the density.
Well, of course, I didn't say flat space. I said Newtonian. But of course, space is flat in Newtonian physics.
Right. So if it weren't flat, you'd have to make some adjustments to the equation?
Nope.
Interesting.
All you have to do is put k back in, either positive, negative, or 0. That's all it takes. The equation itself. Now, I'll explain why in a second. Let me get one more question. Why there should be an equation based on Newtonian physics that should have the full complexity is an interesting question. But yeah, go ahead.
Right now you said that the length of meter sticks doesn't depend on A. At some time long ago, did the length of meter sticks depend on A?
Well, sufficiently long ago, I suppose, the meter sticks were so crowded together that they melted and blended into each other. And the idea of a meter stick, sure, at some point the meter sticks were just about a meter apart. A little before that, they were pushing against each other and got squeezed. There's no such thing as a rigid body in relativity. Remember that? You remember why there can't be a rigid body? If there was a truly rigid body and you hit it on this side, since its length can't change, the other side would instantaneously have to move off. But if that were true, then you could send messages faster than the speed of light. So the other side can't move until light has a chance to get there, and so you know there's no such thing as a truly rigid body.
Why do you think there is this coincidence of equations, Newtonian and relativistic?
Well, all right. Here I think is what you can say. When do you expect general relativity to become important in this particular kind of analysis? I'm not going to pick that up. It's when the curvature of space becomes important. It's kind of like the Earth. When does the curvature of the Earth become important? When you're studying regions of the Earth which are of order of magnitude the radius of the Earth. If you study a small little patch of Earth, then you needn't worry about the curvature of the Earth. Now, supposing we're interested in the question, how does grass grow? Do we have to worry about the curvature of the Earth to figure out the principles of the growing of grass? No. Why? Because grass is, the distance between little bits of grass is a lot smaller than the radius of curvature of the Earth. As long as we're studying cosmology on distance scales smaller than the radius of curvature of the whole universe, that's supposed to be the whole universe thought of as a giant three-dimensional sphere or something else, we can still study little portions of it, which may have many galaxies, and the study of a little portion of it on a scale smaller than the total radius of curvature will be a good approximation. And the smaller the region, the better the approximation. We can do it by Newtonian mechanics. Newtonian mechanics assumes two things. Okay, it assumes two things. The first thing is that the curvature of space is, on the whole, is not important in the problem. That gets rid of general relativity. The second thing is nothing is moving very fast near the speed of light. Now, as long as I study a small enough region and use the Hubble law that velocity is Hubble times distance, as long as the distance is not so large that the velocity gets up near the speed of light, then the equations that we've written down are correct. Well, the equations we wrote down gave us an answer, and you can think of that answer as how the scale factor evolves with time, as seen by only looking, if the Earth were to suddenly start expanding uniformly, and we go out in a field, we could measure the precise behavior of the expansion of the radius of the Earth without ever measuring the radius of the Earth itself and without even realizing that the Earth was curved. We would just watch how the grass blades increase the distance between them. So as long as the distance is small enough that the relative distance between blades of grass doesn't grow with the speed of light, and as long as the curvature of the Earth is not important, we can study things in the small. And that's what this is. This is the study of cosmology on distance scales small enough that we don't get near the speed of light, and small enough so that the curvature, radius of curvature is important.
Does our Hubble volume meet both of those? Meets the first, right, as far as we know?
The only thing that's important is that there be a scale which is big enough so that things are homogeneous and small enough so that curvature and velocity are not depreciable. All right? So there is such a scale, a few million light years on a side, where the speed of receding velocities is still much smaller than the speed of light, and in which is still much smaller than the radius of curvature. So we just take that region and we study it, and we say it's good enough to do it by Newtonian physics.
To the extent that h is to be considered a constant, doesn't b eventually become speed of light?
Eventually, but as long as we study things on smaller scales than that, we're okay. Yep. We go out far enough, and things will be receding with the speed of light.
But that doesn't explain why there's a term in this Newtonian equation that it corresponds to curvature.
But there is a term. Right. Right. We'll get there. We'll get there. We'll get there. Next time we'll talk about curvature. We'll talk about the curvature of space, and we'll talk about Einstein's equations and the relation between Einstein's equations and Newton's equations. Basically, as you might expect, plus or minus, I can't remember, k divided by a squared, this is one of the Einstein equations. Here, let's just look at it. K is a number. K is a number, a pure number. Okay, so A dot over A squared minus K over A squared. This has to do with geometry. It has to do with how the universe is expanding. It has to do with the metric. A is connected with the metric of space. So what's on the left-hand side, I've transposed this to the left-hand side over here. Plus or minus, probably plus. What's on this side here has to do with geometry, the geometry of expansion. What's on the right-hand side has to do with energy density, m over a cubed. Well, why am I writing an m over a cubed? It's 8 pi g times the energy density. Why energy density? Mass and energy are the same thing. This is clearly one of the Einstein equations that connects on the left-hand side geometry with the right-hand side, which is energy density. All right. So another way to derive exactly the same equation is to write down the Einstein equations and simply plug in our assumptions. Our assumptions, homogeneous, uniformly expanding. Plug in this metric with an arbitrary time dependence. Calculate the curvature, calculate the Einstein tensor, put it on the left side. On the right-hand side, put the energy density. And that becomes Einstein's equations. So, and I think that's the way the equations were first discovered. Not by, I think it was, as far as I know, it came later that people interpreted these equations in terms of Newton's equations, I think. I'm not sure of my history there, but I believe that's the case, that they first were derived from general theory. Any other questions? Okay, we'll see you next week.
Thank you.